Radioactivity refers to the spontaneous emission of particles or radiation from unstable atomic nuclei. Be sure to watch our video on isotopes first for background knowledge on radioactive decay. The particles emitted from unstable atomic nuclei during radioactive decay are alpha, beta, and gamma particles. Understanding the characteristics and behaviors of these particles is crucial for safety precautions. An alpha particle is a helium nucleus consisting of 2 protons and 2 neutrons. Since protons are positively charged and neutrons are neutral, the overall charge of the alpha particle is +2. Since it consists of 4 nucleons, it has an atomic mass of 4. A beta particle is a fast-moving electron, therefore it has a charge of -1. Electrons have a much lower mass than protons and neutrons, which is negligible. Gamma radiation is an electromagnetic wave consisting of photons which travel at the speed of light. Photons have no charge and no mass. Alpha radiation is the least penetrating and can be stopped by a sheet of paper. Beta radiation can be stopped by an aluminium sheet of a few millimeters. Gamma radiation is the most penetrating, and even several centimeters of lead will not stop it completely. Now, let's discuss how the particles deflect in electric and magnetic fields. Deflection refers to the change in direction of movement as a result of a force. In an electric field, positively charged alpha particles are deflected toward the negative electrode, and negatively charged beta particles are deflected toward the positive electrode. Gamma rays are not deflected because they have no charge. Alpha and beta particles are also deflected in magnetic fields, in opposite directions, and again gamma rays are not deflected. These radioactive particles can damage or even kill living cells. Therefore, safety precautions are crucial when handling radioactive substances. When working with radioactive samples, warning signs must be posted in work and storage areas. Wear protective clothing, such as a hazmat suit, gloves, and closed shoes. A breathing mask is also used to prevent breathing in radioactive particles. A hazmat suit is a full-body, impermeable suit that reduces exposure to radiation. However, these suits do not protect against exposure to gamma rays. Even when wearing protective clothing, you should still keep as far away as possible from radioactive material by using tools, such as tongs. Do not work with radioactive material for long periods of time. Exposure time must be kept as short as possible. All radioactive material should be stored in lead-lined containers that clearly display hazard labels. You should place shielding around the radioactive material if possible. Glass of a few millimeters is good protection for most beta sources. Lead shielding is necessary for gamma radiation sources. Dispose of radioactive waste properly by storing it in thick metal containers and burying it underground. The storage containers must have hazard labels stating that the material is radioactive. Background radioactivity is low-intensity radiation present in the atmosphere. This radiation is constantly in the surrounding even when not using radioactive materials and are caused by cosmic rays, earth minerals, nuclear fallout, medical rays, etc. Cosmic rays refer to radiation from outer space. Earth mineral radiation is from the Earth's crust, which contain radioactive elements, such as radon gas. Nuclear fallout refers to emission from nuclear experiments and nuclear power stations or nuclear fuel reprocessing accidents. And medical ray emission is from medical procedures such as X-rays or nuclear medicine. Detection of radiation is based on the fact that when radiation passes close to or through an atom, it knocks out electrons, ionizing the atom. Radiation detectors work by detecting the presence of these ions that they produce. A GM counter is a device that produces an electric current when in contact with a radioactive material. It consists of a cylindrical metal tube filled with a low-pressure gas such as argon, a thin mica window, thin metal wire, a high-voltage supply, and a counter or scaler. This is how it works. Radiation enters the tube through the thin mica window, ionizing the atoms of the gas and removing electrons from the gas atom. The gas atom becomes a positively charged ion, which moves toward the negatively charged metal tube. The negative ion, which is the removed electron, flows to the positively charged central metal wire, which produces electric current. The current flows to the counting device that shows a measure of radioactivity. More counts per second means a higher radiation. Another radioactive detector is the cloud chamber, which produces images to show the presence of radiation. It consists of a plastic or glass container that sits on dry ice, a dark material such as a sponge soaked in alcohol, radioactive material, and a detachable lid. Here's how it works. As radiation passes through the chamber of cold alcohol vapor, ions are formed and vapor condenses on them, leaving a visible trail of droplets. Alpha particles leave bold and straight tracks, whereas beta particles and gamma rays leave much fainter tracks. The half-life of a radioactive material refers to the time it takes for half of the radioactive nuclei to decay. So, if you have a sample of 48 radioactive nuclei, the half-life is the time it takes for 24 nuclei to decay, and after that the same amount of time will be taken for 12 radioactive nuclei to decay, and so on. All radioactive atoms have different half-lives. The half-life for one kind of uranium-238 is over 4 billion years. For radium-226, it is 1,600 years. For polonium-199, it is 4.17 minutes, while for polonium-197, it is 53.6 seconds. It is important to know the half-life of a radioactive isotope so that you know when it is safe to handle. Most radioactive materials are safe to handle after 10 half-lives. Half-life decay rates can be used to determine the age of fossils and artifacts. The half-life of an isotope can be calculated once the initial mass of the radioactive isotope is known, and the mass of the remaining radioactive isotope after a certain period of time is also known. The following equation can be used to calculate the half-life of a radioactive isotope. Half-life equals the period of time over the log base 2 of the mass of radioactive isotope before decay over mass of the radioactive isotope after a certain period of time. Now, let's work out an example. A sample of titanium contains 0.6 grams of titanium-44. After 100 years, 0.189 grams of titanium-44 remains. Determine the half-life of titanium-44. Pause the video to first try it out yourself. So, if you substitute the correct values, you will find that the half-life of titanium-44 is 60 years. Now, if you know the half-life of an isotope and the mass of the sample, you can also calculate the mass of the isotope that will still be radioactive after a certain number of time, using the following equation. Let's use this equation to work out an example. Fluorine-20 has a half-life of 11 seconds. If a sample initially contains 6 grams of fluorine-20, how much radioactive fluorine remains after 20 seconds? Pause the video to work it out first. So, with the correct substitutions, you will find that the mass of fluorine-20 remaining after 20 seconds is 1.7 grams. And there you have it, a glimpse into the world of radioactivity. I appreciate you for joining me on this exploration. Be sure to like and subscribe for more. As you navigate the wonders of science, always prioritize safety and let your curiosity guide you. Thanks for watching.